I'm going to talk about evaluating multi-agent training algorithms. We heard from Bo Wagner this morning that AI is in an evaluation crisis, so I think no further motivation is necessary. This is joint work with my student, Zun Lee. I'm in bold here because I'm here giving the talk. Zun had all the new ideas and did all the work.
And just click on it. I'll try it. Now, oh no. Now there it should work. Okay. And even that might.
Okay, good. The claim here is this is relevant to really evaluating any advanced interactive AI. So I'm not going to say much that's specific to language models here, but language models certainly qualify as interactive, and multi-agent training applies. So finding the problem, assessing the performance of complex learning systems that are going to somehow interact with humans or other AIs. My voice quality is poor. That's pretty harsh. Okay. Now I'm going to talk about two particular complications that come up. One is extreme uncertainty due to the complexity and lots of stochastic factors involved here. And the other is specific to the strategic dimension because they're interactive. Now, the uncertainty part of this comes up in single agent problems, and it's dealt with routinely in single agent RL, not necessarily to say that it's a solved problem, but these work in domains that have a lot of stochasticity in the environment as well as in the learning algorithm. There might be different initial conditions, hyperparameters, all these things complicate that as well as the randomness. So here's a typical chart you'll see. This is from the OpenAI paper on PPO. You try your method on various domains. Here's from one domain, and then you try it with different random seeds, and you draw error bars based on how that comes out differently. Pretty well behaved in this case. When you add the strategic issues, now the performance depends not only on all these stochastic parameters and the initial conditions, et cetera, but on the other agents context. And you might be tempted to make a worst case condition. I want to work in a Byzantine environment where the other agents are arbitrarily malicious or harmful or whatever, but that's going to just trivialize any conclusions you get in realistic domains. Maybe I can move to a quieter location. And moreover, what comes out of a multi-agent training regime, it obviously tried things in some multi-agent contexts, but whether they did it consistently or actually even, they're very opaque actually about what was the regime by which they varied what the other agents were doing when you were learning, say, what a particular agent should do. So we want robustness. We want to come up with learned policies that work well with some variation of the other agents. However, we don't, some matter more than others, right? We may not care how well we do against random agents or agents that are really stupid, but you don't want to optimize to necessarily anything in particular. So that's quite a tricky problem. We can make the problem pretty well defined by considering multi-agent reinforcement learning as a form of game solving. So once you take that perspective, your objective here is to do multi-agent learning to give you the solution to a game. Then you're measuring how well the method converges to a solution to the game. And so this is, our papers all have graphs that look like this, and DeepMind's papers have this. This is from some recent work of Max Smith, and you can see this chart on his poster later today, and he'll explain it to you. But what it shows here is trying different methods as a function of time, how the regret goes, regret here being a measure of distance to Nash equilibrium. Okay, so how they're converging to a Nash equilibrium. There's various issues with this. One is measuring regret, even in an experimental setting, can be quite tricky because you have to be able to come up with an exact best response to any particular situation all the time. This tells you about convergence to some equilibrium or approximate equilibrium, but it doesn't tell you anything about which equilibrium. It doesn't, and maybe you actually don't want to just find one equilibrium, you want to find whole equilibria, or you want to cover some set of equilibria. So this doesn't really say anything about that. And another just generalized issue is it's taking the perspective of a game solver who kind of sees all the agents or cares about all of them, and and thinks about this, the game is going to have some kind of correspond to whatever solution concept the game solver cares about, and that may not always be right. Okay, nevertheless, we do this. When we do this, we then can evaluate the different strategies. Well, we need some measure. We use something called NE regret, Nash equilibrium regret, which is defined as how much loss you have by playing your policy pi instead of the equilibrium policy when everyone else is playing the equilibrium. Okay? This basically is taking the assumption that what we care, the most relevant other agent context is when everyone else is rational, okay, according to a particular equilibrium. We've been using this for a while. There was a paper a few years ago by Balducci and others, reevaluating evaluation. Very interesting paper that looks at evaluation in a broad way. They come up with something called Nash averaging, which is basically, it's equivalent to NE regret. They have an axiomatic context for two-player zero-sum that they argue why it's the best one there. One big issue with it is that it is sensitive to the choice of the equilibrium. If there's a game with multiple equilibria, you're going to get different answers for any regret depending on which one you picked. Balducci argued for max entropy Nash, which still doesn't get you to uniqueness, but it narrows it down a lot. And you can argue that that's, if you have to pick something, that might be a pretty good choice. We're going to pick it here. I'm going to illustrate this whole thing in the context of a two-player sequential bargaining game that's become popular for a lot of recent work. We have some set of items that the two players are negotiating about how to split. They have different valuations for the various items. It's an alternating offer protocol. They go back and forth making offers, and it goes until either one accepts the other's offer or you run out of rounds, T rounds max. This game is a general sum game because they have different valuation functions for the items. It's imperfect information. There's private values plus, there's private values. And that makes it a very challenging game. With these particular parameters, there's 10 to the 12 information sets. It's a very large game. You don't expect to just solve it analytically. Okay, so the things that we're going to evaluate, we're calling multi-agent training algorithms, or MADAs. A MADA maps a game environment plus a random seed to some game solution, which is going to be a strategy profile or a joint policy for all the agents. Okay, that's what a MADA does. It's a meta strategy because it takes one of its inputs is a game, so it really maps. So unfortunately, the term meta strategy gets used often for just strategies, but this really is something that maps games to strategies. So if we have meta strategies, that suggests that we can form a meta game. So this is a game among the meta strategies, and you can think of you have M metas that you could apply to various games, and you can build this big matrix where you consider player 1 is playing one of the metas, player 2 is playing the other meta, and there's randomness because they can choose different random seeds. Okay, this is meant to represent the kind of space of seeds they can be picking from, and the cells are the expectations over payoffs with respect to the random seeds, right? So depending on the randomness, they can get different outcomes, but we get expectations. Yes. Kevin?
Didn't you say that MADAs map to joint strategies?
Yes.
So
yes.
teach you to map to a joint strategy.
Exactly. So MADA 2 will come up with a joint strategy, but then if it's playing player 2, we'll only pick player 2s. So they map to joint strategies. That's why you can have a MADA 2 playing either row or column player, because they're going to come up with both of those.
Isn't that kind of functionally the same as a MADA just generating only one agent's strategy?
You can have non-symmetric versions where they do that too. We're picking the symmetric. This makes it easier to always deal with symmetric games. Symmetric games among MADA. You can have MADA to specialize only in certain roles of the game. That would be fine. Okay, I mentioned the issue of uncertainty. So that's the random seeds. So we have, they're going to pick different random seeds. We could come up with a game where if they pick the first random seed, they'll get a certain payoff. We can form an empirical payoff matrix based on a particular draw of random seeds. And we can compute some statistic of interest, like any regret, as I'll mention. And we can do that for lots of different random seeds. And that will give us potentially a distribution over the statistic of interest. Okay, now we don't want to just do it for individual seeds. So what we actually do is this bootstrap approach, where if we are going to, in our evaluation, run many random seeds for each one, what we're going to do is we're going to take the basic idealized metagame that has the expectations. We're going to resample from each of those with replacement, make another empirical game. Right? We solve the first one to get the solution, and we can then compute the regret of the solution in the resampled game, and that gives us one more point on the bootstrap distribution of the statistic of interest. Any regret. So for example, this regret. So the reason it's complicated, regret is a very nonlinear function of the whole game matrix. So we have to resample over the whole game matrix to get one data point for regret. Okay, and then we can get confidence bounds on regret by looking at places on that distribution. Okay, so in what I'm going to show you, we use the max entropy Nash or an approximation of it, because we can't always compute it exactly, as our baseline. We calculate any regret of each pure strategy, and we use that to rank strategies. Another statistic. Statistics don't have to just be numbers. So we also like looking at best response graphs. So if you have a payoff matrix, you can come up with a graph version of the best response relationship. So here's rock, paper, scissors. Paper is a best response to rock. That gives you a little best response graph here. And we can view this as a statistic on the empirical games. And we sample many of those. And then we average the adjacency matrices to give you an average best response graph. OK, so we did this not just in the abstract. Zun came up with a matter that he really wanted to evaluate. It's called Gumbel IS MCTS. I'm not going to get into the details for the purposes of this talk. The substance is not too relevant. But we use it to evaluate a comprehensive, not exhaustive set of the state-of-the-art matters on this bargaining game. Self-play-based methods, population-based methods, methods based on info set search like Gumbel IS MCTS. And we also, in addition to just trying to see which is the best or what, how they relate to each other, we were also interested in just looking at differences between version 1 of an algorithm plus version 2, where they use decision time search to improve their policies they come up with. And here's an example of the results. And I'm certainly not going to go through it. And I'm not even going to tell you what all the different methods are. For one particular instance of that bargaining game, what can I show you? So we have the any regret score, the plus or minus. All of that was the bootstrapping stuff to get those confidence bounds. We also looked at Nash bargaining scores, just another kind of statistic. You could use whatever statistic you want. And so one interesting, so among the high ones are RNAD. That's the regularized Nash dynamics. That's the method that was instrumental in the Stratego milestone from DeepMind a little while ago. And the version with runtime search and without. And if you look at all of the combinations of the method with search and without, the search method did better. Okay, maybe not too surprising, but it really confirmed it across the board. This ranking is by the NE score. The top 4, there's a pretty big gap. So we would probably say we're not going to make a strong conclusion among these, but there was a bit of a gap there. We also looked at some heuristic methods, a tough bargainer, a soft bargainer, a random bargainer. Not surprisingly, they didn't do so well.
But we're not supposed to be evaluating the success of these heuristics. We're supposed to be evaluating the evaluation metric here?
We're evaluating these matters. These are the matters. These are all matters, but these are not policies for the bargaining game. These are ways of learning policies to play a class of bargaining games.
Okay.
Here's the best response graph. And again, you can't really read it, but you can, there's some interesting things like, that tough strategy was a really bad strategy, but it really does well against soft, right? If you really know the other player is going to be a patsy, you just be, tough. The other thing that was a bit we noticed from this is that there's a lot of self edges. Okay, some strength there. So this is suggesting that. So remember, these are the best responses. It's saying often one matter is the best response to itself, and this is why it's good to have them be symmetric here, suggesting that these matters are overfitting to play in themselves. And that's not surprisingly for the self-play-based methods, but even the population-based methods or the other methods. Maybe not too surprising. They're training in an environment where they mostly have looked around the space around the policies they're concerned about, and they're going to do well against those policies in particular. Okay, a similar, yeah?
Uniform beating something?
No, this is just saying this is the thing that is its best response. So fictitious, something is the best response to that.
Okay.
No, an arrow into something is the best response. It's the best response. Okay, and we looked at parametrically, but it turns out it's qualitatively the version of the game. Same top four. There definitely are some differences. Actually, I didn't mention there's also we noticed there's a general the ones that did best on Any Regret also did best on Nash bargaining score. This is just the product score, which makes it's not surprising for a bargaining game. That might be a good indication of how well they do, since it really is a general sum game. Okay, and the similar kind of self-play edges here. So this at least validated in our minds that this was telling us something interesting about, it's a pretty complex set of methods. We didn't totally deliver on the metagame story because I gave you two separate analyses for the two different parametric versions of the game. Actually, you want to look at some kind of distribution of bargaining games and do well on those. And you have to do a training for each instance of that, right? Of course, within each instance, there's still uncertainty about the valuation distribution, so you have to do lots of sampling within that game. It's still a game of incomplete information. But we should look at qualitatively different games that the same models can work on. And there's an idea that just like meta RL is a way of kind of systematizing the search for hyperparameters, we should be doing that in a game context for multi-agent RL, where I think hyperparameter tuning is even more kind of dicey issue. And then at least I should have a large language model on some slide. So we also want to be able to, we would use the same framework for evaluating large language models as bargainers, right? It wouldn't be too much to make one of them play this particular bargaining game, and this is how we would propose to try to evaluate them in this setting. Thank you.
We'll take questions. One comment. Tomorrow, Minnie's going to talk actually on answering this one, so we already saw the
good.
answers. Yeah.
I'm not answering this.
But you did already answer, so. Okay, questions.
Yeah, so a clarification, like so you said you didn't deliver on the doing the thing for the distribution. So what you showed was just for.
No, it was still the metagame, but I didn't show the full power by having that be some kind of combination over the matters trained on several different games.
So it was just one game?
So I showed you two parametric instances of that bargaining game.
Yeah.
And each one was randomized over lots of different combinations of matters and lots of different random seeds. But each metagame was just for that one particular game class. We could easily average them over the two and report those statistics.
The metagame being the main drag.
It's still, the metagame is the game over matters. Right, the distinction here is this game over matters instead of a game over policies in the game. Right, the MATA is the training algorithm, which is going to produce a range of different policies depending on the random seed, depending on all kinds of other stuff.
Okay, and then also, so is it correct my understanding that even if the class of games is all zero sum, that if you had some meta that always produces a Nash equilibrium, it's not necessarily going to be at the top of that table.
So I think that's true. I say I'm not sure. Yeah, and you know, this is motivated especially by games that are not zero sum, because where equilibrium selection is more of an issue, and which is and most of the games that we care about, all the games that I care about are not zero sum.
Yes, you did mention in one of the slides saying that we should be evaluating things on a variety of games. So I just want to ask, does this choice of games influence the evaluation? For example, say we choose sequential bargaining games. Also, we choose some other, so for example, monotone games or bulk of games. So, do you see any influences from those choices?
Yeah. So this I think gives us a way. Yes, and I think we want to be able to understand how varying the set of games does things. I mean, look, we had RNAD there, right? RNAD made its name by doing this great thing in Stratego. Now, if it was only good at Stratego, we wouldn't. Who cares? Right? There was an implicit claim that the techniques were generalizable beyond that. So here, we can try it on some other things, but not near the breadth that you'd want to have real confidence that a method was really going to be good across qualitative different games.
Can I ask a little bit about the issue of multiple equilibria in this evaluation? I was just having, and those was really crucial for me in language because you speak French or English, and I wasn't just having an easy time tracking how those equilibrium were getting selected and how that was impacting the score.
So here we based it on the max entropy equilibrium. That was our way of selecting.
Are those in this game?
Well, there's probably there may be, since we only are approximating that anyway. There certainly are many. They're probably not too different, but they could be, and especially I mean, if we bring in games like these language games like we've been talking about today, there's going to be arbitrary coordination aspects, and this is why this shows you this tendency to overfit to yourself in matas is going to be a real issue, right? We want to put out multi-agent training algorithms, and we can't assume that all the other agents in the world were trained with the same methods, right? There's no way around that, and so this is not a solution to the equilibrium solving problem. It maybe means we need be more creative about how to do on-the-fly coordination, all those other things, so that would be erased.
Question about the generalization of this. So the example you're talking about more about this finite strategy space. Is it possible to generalize this framework to continuous strategies or even more complex?
So I don't think there's anything importantly finite. I mean, the policy space in these games is vast. So if you had continuous parameters, you're still using RL methods that are only going to be selectively exploring the relevant space. So I don't.
Awesome.
Okay.
Thanks so much.